When most people first encounter Linux, they experience it through what we might call a traditional distribution. Maybe it's Ubuntu, maybe it's Fedora, maybe it's Arch. You install it, boot into a desktop, open a terminal, and start installing packages. You tweak configuration files and etc. You enable services, you install drivers, you customize your shell, and over time your system becomes uniquely yours. It's powerful, flexible, and often empowering. But it's also fragile in ways we don't always notice until something breaks. Now imagine a different model. Instead of manually shaping your system step by step, you describe the entire system in a single configuration file. Not just which desktop environment you want, but which services should run, which users exist, which packages are installed globally, how networking behaves, how your bootloader is configured, even how your kernel is built. You don't mutate your system piece by piece. You declare what you want it to be. And then the system builds itself to match that declaration. That is the core idea behind NixOS. The contrast between NixOS and traditional Linux distributions is not just about different tools. It's about two fundamentally different philosophies: imperative versus declarative system management. In traditional Linux, you tell the system what to do, step by step. In NixOS, you describe what the final state should look like, and the system figures out how to get there. This difference might sound subtle at first, but it has enormous implications for reliability, reproducibility, collaboration, and long-term maintenance. Let's start with how traditional Linux systems evolve over time. You install packages using a package manager like apt, dnf, pacman, or zipper. Each package places files into standard system directories, /usr/bin, /usr/lib, etc., and so on. When you change a configuration, you edit files directly. When you enable a service, you run a command. When you upgrade the system, new packages overwrite old files in place. The system state is the result of everything you've done to it, every command, every tweak, every experiment. Over months or years, it becomes a unique artifact of your personal history. This model is intuitive because it mirrors how we think about interacting with computers. We install something, configure it, test it, adjust it, and move on. But the downside is that the system state becomes difficult to reason about. If something breaks, you may not remember which change caused it. If you want to replicate your setup on another machine, you must manually recreate every step or rely on partial solutions like scripts or .file repositories. Even then, subtle differences creep in. A slightly different package version, a forgotten configuration tweak, a dependency that changed upstream, these can all lead to unexpected behavior. NixOS takes a radically different approach. Instead of modifying the system in place, it treats the entire operating system as a build artifact derived from a configuration. At the heart of NixOS is the Nix package manager, which uses a purely functional model. Packages are built in isolation and stored in unique directories in the Nix store, typically under Nix store. Each package path includes a cryptographic hash that reflects its build inputs. If two packages differ in any dependency or configuration option, they get different paths. They do not overwrite each other. They coexist. This design eliminates one of the biggest sources of instability in traditional systems: global state mutation. On a traditional system, upgrading a library might silently affect every application that depends on it. On NixOS, multiple versions of the same library can exist side by side, and each application uses the version it was built with. There is no shared global directory where files get replaced. Instead, each build is isolated and self-contained. The declarative nature of NixOS becomes most visible in its configuration model. In a file typically called configuration.nix, you describe your system in a structured, declarative language. You might specify that you want the GNOME desktop environment, the OpenSSH service enabled, a specific firewall configuration, a particular version of the Linux kernel, and a list of system packages. When you run the rebuild command, NixOS evaluates this configuration and builds a new system generation that matches your description. It doesn't mutate the current system directly. It constructs a new one alongside the old. This leads to one of the most celebrated features of NixOS: atomic upgrades and rollbacks. Each time you rebuild, you create a new system generation. The bootloader is updated to include this new generation as an option. If something goes wrong, you can simply reboot into a previous generation. No complex rescue procedures, no hoping you can undo a broken package upgrade. The old system still exists, untouched, ready to be used. This is a profound shift in how we think about system stability. In traditional Linux distributions, rollbacks are often partial or difficult. Some package managers keep caches of old versions, but configuration changes are usually not tracked in a coherent way. If you upgrade your system and it breaks, you may need to manually downgrade packages, restore configuration files from backups, or even reinstall the system. With NixOS, rollback is built into the core design. It's not an afterthought. It's a natural consequence of the immutable, generation-based model. Reproducibility is another major advantage. In traditional Linux, documenting a setup often involves writing long installation guides or scripts. Even then, results can vary depending on the base system, repository state, or subtle environmental differences. In NixOS, the configuration file is the documentation. It is the single source of truth. If you share your configuration with someone else and they build it on their machine, they should get the same system. This is incredibly powerful for teams, developers, and infrastructure management. Imagine a development team working on a complex project with multiple dependencies, specific versions of compilers, libraries, language runtimes, and tools. On a traditional system, ensuring that every developer has the exact same environment can be a challenge. You might use containers, virtual machines, or elaborate setup scripts. With Nix and NixOS, you can define the entire development environment declaratively. Every dependency is pinned. Every tool version is specified. The environment is reproducible by design. This declarative model also changes how we think about configuration management at scale. In the server world, tools like Ansible, Puppet, and Chef emerged to manage large fleets of machines. They attempt to impose a desired state on systems that were not originally designed to be declarative. They run scripts that install packages, edit files, and enable services, trying to converge the system toward a defined state. NixOS, by contrast, starts from the premise that the entire system is defined declaratively from the beginning. There is no need to bolt on a configuration management layer to achieve reproducibility. It's inherent. However, this power comes with trade-offs. NixOS has a steep learning curve. The Nix language is not like Bash Python or YAML. It has its own syntax, semantics, and functional programming concepts. For newcomers, writing a configuration file can feel intimidating. The error messages can be cryptic. The documentation, while improving, often assumes a certain level of familiarity with functional thinking. In contrast, traditional Linux distributions benefit from decades of tutorials, community guides, and shared conventions. Another difference lies in how you install and manage software. On a traditional system, you run a command to install a package, and it becomes available system-wide. On NixOS, you can install packages declaratively in your configuration file or use user-level environments with Nix profiles. The distinction between system packages and user packages is more explicit. This can feel restrictive at first, but it also encourages discipline. Instead of casually installing random tools and forgetting about them, you're more likely to add them to your configuration, making your system's state explicit and reproducible. The isolation model of Nix also addresses the infamous dependency hell problem in a novel way. Traditional package managers try to resolve dependencies globally. If two applications require incompatible versions of a library, you may be stuck. Nix sidesteps this by allowing multiple versions to coexist. Each package is built against specific dependencies and stored in a unique path. There is no need to force a single version for the entire system. This dramatically reduces conflicts. Performance and storage concerns sometimes arise with this model. Because Nix stores multiple versions of packages, disk usage can grow. However, Nix also provides garbage collection mechanisms to remove unused packages and old generations. While the store may look large, much of it is shared between builds. Identical dependencies are reused, and only differences result in new paths. In practice, the overhead is often manageable, especially given modern storage capacities. From a philosophical standpoint, NixOS challenges the traditional Unix mindset in subtle ways. Unix has long emphasized small tools, composability, and direct manipulation of text files. NixOS doesn't reject these ideas, but it abstracts them into a higher-level model. Instead of editing dozens of configuration files scattered across the file system, you centralize your system's definition. Instead of relying on mutable state, you rely on immutable builds. It's still Linux underneath, but the way you interact with it changes fundamentally. For desktop users, the benefits can be transformative. Imagine customizing your entire desktop environment window manager, themes, fonts, services, keyboard layouts, and knowing that you can recreate it perfectly on any machine by copying a single configuration repository. If you experiment with a new setup and dislike it, you can revert instantly. Your system becomes less of a fragile snowflake and more of a reproducible artifact. For developers, Mix's approach to environments is especially compelling. You can define project-specific environments that don't interfere with the rest of your system. You can pin dependencies to exact versions. You can ensure that a project built today will build the same way months or years later. This is not just convenience. It's a solution to a deep problem in software engineering, the drift between environments over time. Traditional Linux distributions are not inherently flawed. They have proven themselves over decades. They are often simpler to understand initially. They align well with how most tutorials and software assume systems behave. For many users, especially those who prefer a more hands-on, incremental approach, traditional distributions may feel more natural. They offer flexibility without requiring a paradigm shift. But as systems grow more complex and as reproducibility becomes more important, whether in development, research, or infrastructure, the limitations of the imperative model become more apparent. The declarative model of NixOS addresses these limitations at a foundational level. It doesn't try to patch over them. It reimagines how an operating system can be managed. In the end, the debate between NixOS and traditional Linux is not about which is universally better. It's about what trade-offs you are willing to accept. NixOS demands that you learn a new language, adopt a new mental model, and embrace a more structured way of managing your system. In return, it offers reproducibility, rollback, isolation, and a level of control that is difficult to achieve otherwise. Declarative systems matter because they reduce uncertainty. They make systems predictable. They turn configuration into code and state into something you can reason about. In a world where software complexity continues to grow, that predictability is not a luxury, it's a necessity. And NixOS stands as one of the most ambitious attempts to bring that necessity to the very foundation of the operating system itself.